Hi, everyone. Thanks, Jim, for the introduction. As Jim said, I came to Array from NREL, but I largely worked on cell level research in cadmium telluride solar cells. So it's been I joined Array in March of this year. So it's been a pretty big transformation for me. The work that I'm presenting is, I was down in a dungeon of a lab when this was done. So I'm not taking credit for it, but I hope I can do it justice. So it's the work of Kyumin Lee, Kendra Conrad, Daniel Fusaro, and Sanket Shah. So the title is Evaluating Energy Gains on Intelligent Tracker Control Algorithms with Alternating A/B Tests. So I'll start by giving a brief overview of two SmarTrack platform features, which include SmarTrack Backtracking and SmarTrack Diffuse. The bulk of the presentation will be focused on Array's validation strategy for new SmarTrack features, which includes utility scale field evaluations combined with an alternating operation procedure, and I'll touch a little bit on modeling. I'll be showing gain evaluation examples for two sites that were validated by a third party. And I'd like to stress that while I'm only showing two examples of SmarTrack features, they have been deployed on over 1 gigawatt of capacity. Also, we perform a gain evaluation for each customer site, similar to the examples that I'll be presenting today. So we have, I'll be presenting on two features. We have SmarTrack Backtracking, which is an alternative backtracking model. It considers the site slope and row height variations, and it's combined with a procedure to learn the underlying model parameters. SmarTrack Diffuse is a unique algorithm that moves the trackers to a flatter position to increase the irradiance on the modules during persistently cloudy conditions. So this is related to the first talk that we heard today. So the backtracking problem, so shown in the top right, is the true tracking strategy that results in row-to-row shading when the sun is low in the sky in the early morning and late afternoon hours. So that the shading can drastically reduce the electrical output of crystalline silicon modules due to the architecture. So the shading can be eliminated by moving the modules to a flatter position, but at the expense of angle of incidence losses. So the generic tracking model developed, or backtracking model developed in the 90s, positions the modules to eliminate the shading while minimizing the angle of incidence losses. However, this generic model doesn't consider the site slope or row height variations. So when I say row height variations, I'm talking about generally talking about construction tolerances from row to row. So using this generic model on a site that's not perfectly flat or has construction errors can result in shading losses. And I wanted to just note here that at Array we have a term projected solar zenith, which is just equivalent to the true tracking angle, but you'll see that in a couple of the slides. We talk about three backtracking strategies. The first uses the generic backtracking model with what we're calling the baseline. It uses the generic backtracking model with layout row spacing directly off documents. So it doesn't consider the site slope, which will result in shading losses for an upslope and angle of incidence losses for downslope. So this baseline case is represented with the gray line. So it turns out that you can tweak the row spacing parameter in this generic backtracking model to reduce but not eliminate shading. So this is what Array's commissioning team does. This is the blue line in the plot. And you can see how the tweak changes the shape of the tracking curve. SmarTrack uses a model that accounts for the cross-axis slope and row height variations and can provide an additional gain relative to the commission case. It uses a proprietary process to learn the underlying model parameters for each motor block without adding hardware to the system. So you can see that rather than changing the shape of the baseline curve, the SmarTrack curve simply appears shifted, which represents the optimum position at each point. So compared to the commission curve, you can see that is at a shallower angle in the morning, which means that the commission curve was still experiencing some shading. At this crossover point, the commission case comes out of shade and then a sun gap develops, and that's leaving some potential production on the table. So this is the source of, apologies, of energy gain for SmarTrack. So when we talk about the SmarTrack gain, we're talking about comparing SmarTrack to commissioned, which has this row spacing tweak, not SmarTrack to baseline. So, and then SmarTrack Diffuse. So under cloudy conditions, as we covered earlier, the tracker angle that maximizes the irradiance on the modules may be flatter than the true tracking or backtracking angles. So SmarTrack Diffuse uses data from the customer's GHI sensors on site to determine when it's advantageous to move the trackers to a flatter, what we call diffuse stow position. So the algorithm resumes normal tracking when conditions clear, and it includes a lot of logic to minimize the risk of false positives, and we have some filters or some checks to catch sensor quality, or to check on sensor quality. So this A/B test, so we use an alternating operation procedure to compare the energy produced by SmarTrack relative to baseline or commission case. So the inverters on the site are divided into two groups, even and odd, and they should have roughly equal capacity. So each inverter alternates between two modes of operation based on the day of the year. So for example, on odd days of the year, odd inverters operate with SmarTrack backtracking, while even inverters operate with commission backtracking. Sorry. So on even days of the year, the two groups switch. So odd inverters operate with commission backtracking, and even inverters operate with SmarTrack backtracking. So we use an analogous procedure for SmarTrack Diffuse, in which the diffuse stow algorithm is either enabled or disabled. And so I hope I'll show that this method allows for DC differences in the two groups to average out over time. This particular SmarTrack backtracking field evaluation took place in the fall of 2020. Site was located in Albuquerque and had an annual diffuse fraction of about 0.26. The test included 16 motor blocks using Array's DuraTrack HC-B3 trackers with 4 central inverters. Importantly, the site had a 2% downhill slope to the east. Sorry, I don't know why it keeps skipping on me. An initial period of 15 days was required to learn the underlying model parameters for SmarTrack. And then backtracking alternating operation was conducted over a 15-day period. So generally speaking, this learning process that I'm talking about can take as little as 2 days if the conditions are clear. But in this case, it took longer due to mixed weather. So the data that were collected are inverter input, DC voltage and current, weather data, and tracker data. So this slide shows the inverter power data collected over the evaluation period. In addition to the SmarTrack versus commissioned alternating operation that we use to evaluate SmarTrack gains on all of our sites, on this site we're able to perform alternating operation testing for SmarTrack versus baseline and commission versus baseline. Apologies, keep skipping as well. So the analysis for these three tests vary to avoid too much power loss from the baseline for our customers. So baseline tracking or backtracking results in a lot of losses. But what mattered most was that we had at least one even and one odd day. This slide compares the power for inverters using SmarTrack Backtracking in orange and the inverters using commission backtracking in blue. Again, it's our stance that this is the most representative metric for the SmarTrack gain, comparing SmarTrack to commission and not SmarTrack to baseline. So the energy gain is defined as the cumulative production by SmarTrack inverters over the cumulative production by commission inverters. So with this alternating operation, that means that on odd days, the SmarTrack sum includes production from inverters 1 and 3, and on even days, the production includes inverters 2 and 4, and so on. So the data show a gain of 1.76% in the morning and 2.33% in the afternoon for an overall average gain of 2.04%. Yeah, and you can really see the gains in the form of these wider shoulders here. So as stated on the previous slide, the SmarTrack versus commission gain was 2.04%. So the manual tweaks that our commissioning team does also resulted in a 2.53% gain relative to baseline. And then the SmarTrack gain relative to baseline was 4.42%, and that number is in good agreement with the sum of the SmarTrack versus commission and commission versus baseline gains. So here we have some images showing what you may actually be able to see in the field after SmarTrack is implemented. This image is an example of commissions operating during backtracking. So it's not showing shading, but you can see this uncaptured light, uncaptured sunlight apparent in these sunbands on the ground. And this is an image or an example of SmarTrack backtracking. So it still shows no shading, but now you see only minimal sunbands on the ground. And then here we just contrast the two, one image side by side. Moving on to SmarTrack Diffuse. So this Diffuse evaluation took place from April to July 2021. The site was located in New York and had an annual diffuse fraction of between 0.3 and 0.4. The test included 7 central inverters, 6 for the evaluation. The test period was 68 days, and it's 58 days when you exclude 10 days of inverter issues. Again, the data collected were inverter input, DC voltage and current data, weather data, and tracker data. Busy slides coming up. So this slide summarizes the diffuse field evaluation data. The top graph shows that the average DC output as a function of time. So the DC output averaged at each time stamp throughout this evaluation period for SmarTrack Diffuse and the baseline relative to the baseline inverted group. So in this case, baseline just means that, okay, that the algorithm was not activated. Just regular tracking, backtracking. So the middle graph shows the average GHI relative to the clear sky limit. That corresponds to a diffuse fraction of 0.34 during the evaluation period. And the bottom graph shows the number of days in a flatter stow position. The SmarTrack diffuse energy gain can be seen in the morning and afternoon, aligning with the bottom plot that shows when diffuse stow occurred. So, for example, you can see a visible gain around 8 a.m. and the bottom plot shows that around 20 of the days, so about a third of the days, the trackers were in stow at this time. So the total energy gain observed in this test period at the site was 0.64%. So we can also plot the running gain evaluation for each day over the test period. So this plot shows the what you can see is that it shows the cumulative energy gain increasing on cloudy days with lower GHI and more hours spent in diffuse stow. So May 2nd or sorry, May 3rd and 5th, for example. So over the 2-month period, the cumulative gain stabilizes, only increasing or decreasing slightly with consecutive cloudy or clear days. The plot also shows how a sufficiently long evaluation period of over a month is necessary to evaluate this diffuse stow function in contrast with the evaluation of the backtracking optimization that requires only a couple of sunny days. The gain oscillations appearing in the last plot that I showed are also worth mentioning. So the weather was mostly sunny during the May 13th to May 20th period. And the cumulative energy gain number gradually decreased through this period, as you can see here. There are, however, small up and down oscillations in the gain values. And we think these are due to these small DC or measurement differences between the even and odd test groups. Another sunny period occurred from June 15th to June 24th. But you can see here that the cumulative gain oscillations during this period are noticeably smaller than the oscillations observed in the earlier period. So the decrease in oscillations in the cumulative gain at the later period indicates that the alternating operation strategy was effective at canceling out the small DC differences between the groups. So I just have one slide on modeling that shows a nice agreement. So we used Plant Predict to for this particular modeling because it allows we need to perform sub-hourly simulations to simulate the diffuse stow function, and you need to be able to simulate custom tracker angles. So we actually use the GHI from the field evaluation itself, and this just shows that we were able to get good agreements between the simulations and the actual measurements. So in conclusion, so this alternating A/B test we believe is an effective strategy to validate gains in performance due to operational differences on a site. The test is particularly successful at canceling out these group-to-group DC differences in production, so small differences in capacity or losses, measurement differences. So the work showed successful use of the test for SmarTrack Backtracking, which is an alternative backtracking model with learned parameters that accounts for site slope and row height variations. So we saw a significant gain, 2.04% observed for commission backtracking for over commission backtracking for a site in New Mexico, and SmarTrack Diffuse, which is a control algorithm designed to increase production under diffuse conditions. And there we saw an energy gain of 0.64%. And that's my talk. Thank you.